Find the instantaneous rate of change for the function. F of theta is 4 root 2 secant theta minus 3 tangent theta at the location theta equals pi over 4. And we're given some options, 1, 2, 3, 4, or 5. The answer is B. 2. All right. Now, instantaneous rate of change. You'll have to learn at some point, and hopefully you've already picked up, that we have a lot of ways to say the word derivative. So instantaneous rate of change, derivative. Slope of tangent line, derivative. Derivative, derivative. Right? So it's important to say, oh, I know all these things are referring to derivative. So, okay, so we're going to take the derivative and plug in pi over 4. We just learned about trig functions, and they're important. The sine, cosine, secant, tangent, know those by heart. Not just for now. You'll tell it to your kids and your grandkids. You'll be gathered around the fire. And you'll say, let me tell you about the derivative of sine. And it'll be a bonding moment. All right, so derivative of secant, secant tangent. Derivative of tangent, secant squared. And you plug in your point, pi over 4. Secant of pi over 4, square root of 2. Tangent of pi over 4 is 1. And you work it out. So, fairly straightforward. This is the kind of level of computation that we're hoping for the multiple choice on the exam. You know, not a ton, but a little bit. And so, you should be able to do that. All right, so our thought for today. It's not a quote, but it's something I think about. And so it's the following. Math isn't done in some tiny corner of the mind. So you might be thinking like, well, I have my little math brain. You know, as you look at a problem, you're like, there's this little piece of me that does math. Somewhere over here, you know, the left cortex or something. That's the part of me that does math. But that's actually not quite right. You see, it's not this piece that does the math. It's this thing that does the math. It's all of you. You bring your whole self when you're doing mathematics. And so when we, as instructors, when we say, you should, you know, take care of yourself, get lots of sleep, eat good food, get some exercise, have fun, be social. You might be thinking, wow, these people care about me. That's only partly true. We really just want you to be better at math. That's our goal. We're not telling it because we want you to be happy people. We want you to be mathy people. And so if you really want to do your best, make sure you're taking care of yourself. And if you need help, you ask for it. There's no problems with asking for help. Everybody needs help at some point. And I think since we are going into that part of the semester when it feels like there might be a bit more stress, I just want you to make sure you take care of yourself. I want you to do great, and I want you to be your best self. All right, so that was our thought for today. Okay, so let's just get it done. Today, the chain rule. And if the only thing you remember from today is this, then you've done today right. So, what is the chain rule about? Oftentimes, when we look at a function, the way we write it is we have a function inside of a function. And so, it's not just like, function plus function or function times function. There's a function on the inside. So, f of g of x. Say, okay, so how do we handle this situation, this composition of functions? So the rule is, if I want to take the derivative of f of g of x, I take the derivative of the outside function, but I leave the inside as is, pristine, you know, as a record, if you will. Then I multiply at the end by the derivative of the inside. So that is to say, how f changes and how g changes both come into play. But you have to make sure you put it in the right way. So This is a very important rule. Indeed, this rule in some sense is the important rule. The quotient rule can be derived from the chain rule. The product rule, if you go and especially once you hit multivariable calculus, it's a special case of the chain rule. Pretty much everything boils down to chain rule. So that's why we want to get really good at it. Now I have two ways to argue why this is true. So what's one way? Well, definition. The derivative of f of g of x, we plug it into our derivative machinery. You have this g of x plus h, and then you have this, just g of x on the inside. Well, multiply and divide by the same expression. And then you say, hey, this last piece on the end, that's your g prime. Okay, so that's where our g prime is coming from. Now here, what do we have? Well, we have something, g of x plus h, but that's going to go towards g of x. We'll call it, say, z for just a second. So z minus g of x, f of z minus f of g of x. Well, that's, again, a different version of derivative, but it's still a valid way to take a derivative. It's the derivative of f at the location g of x. So this is going to f prime of g of x. Now, this is almost a proof. There's some technicalities, but, we're amongst friends. So we will accept this as a proof. A different way to think about it is we know how to think about what are derivatives. Derivatives, what is it saying? When you dig down to it, the whole idea basically says functions, when you zoom in real close, look flat. They look like lines. Derivatives, that's your instantaneous rate of change, and they're the slopes. So we just have to understand, what does our line look like? And then we have our slope. So we say, well, we know near x equals a that g of x looks like the line g prime of a times x minus a plus g of a. All right, well, that's just because that's what it means to be differentiable, or it means to have a derivative. Near the point y, which is g of a, f of y looks like f prime of g of a times y minus g of a plus f of g of a. Again, that's what it means to be differentiable. So we put them together. What do we mean by put them together? Well, do you see where you see this y? Well, that's your g of a. And so we're going to replace that with this g of x. So we replace that with g prime of a times x minus a plus g of a. Simplify. And then we say, okay, what's our slope? It's our f prime of g of a, which came from here, times our g prime of a, which came from there. All right. But the good news is, you don't have to remember either way to derive it. You just have to know it. So, what's our procedure? Well, step 0. You have to recognize that you have a function in a function. And so to apply this, make sure you understand, hey, do I really need the chain rule? And if I do, what's my inside? What's my outside? So make sure you understand that. Now, once you understand that, you differentiate the outside function, plug the inside function into the derivative from whatever you found from step 1, and then multiplying the outside by the derivative of the inside. Okay, so let's do some warm-up examples. Okay, so here we go. The derivative of e to the 31x. So let's do this in slow motion. Eventually we get to the point where we don't have to do this in slow motion. What is the inside function here? Okay, someone has suggested our inside function is 31x. So the function on the inside is 31x. What's our outside function? So our inside is 31x. Our outside, what was it? E to the power. We'll call it x. We could choose a different symbol, but okay. So, what's the derivative of the outside? What's the derivative of e to the x? E to the x. So we said, okay, we figured out what the inside and outside functions are. We took the derivative of the outside, it's e to the x. So we take e to the x, but we don't write e to the x. We plug in 31x. E to the 31x. Right? This is the f prime of g of x part. What else do we need to do? Multiply by the derivative of the inside. So we multiply by, what's the derivative of 31 times x? 31. More generally, we have the following nice fact. And we're going to do this so often, it's going to become automatic. So this part where we say, oh, what's the inside, what's the outside? That's going to become automatic for us. But I just want to point out, if we take the derivative of e to some function g of x, what will that derivative be? It's e to the g of x times g prime of x. And I forgot to write, this is your g prime of x. Because the outside function in this case is e to the x. Now, with that out of the way, I want to take the derivative of something else. Okay, so I'm going to take the derivative now of e to the x raised to the power 31. Whoa, someone said, whoa, same thing. Is it? Well, let's find out. What's the inside function here? The inside function is e to the x. What's the outside function? What? Yeah, something to the 31st power. Okay. Huh. Well, that's weird. Doesn't look the same. Will we get a similar answer, though? Okay, so let's talk about what's the derivative of the outside function? What's the derivative of x to the power of 31? 31 x to the power 30. But we don't put x here. What do we put? E to the x. Why e to the x? Because that's the inside. So again, this is our f prime of g of x. What do we multiply it by? By e to the x. Why e to the x? Because that's the derivative of the inside. Now, do these two match? Well, notice this says 31e to the 30x times e to the x. If I have e to the 30x times e to the x, what does that give? It gives e to the 31x. So they both match. So even though we applied the rules in a different way, and we had a different perspective on saying, oh, well, this way we think of it as, well, here's the inside, here's the outside, we'll still get the same answer. So there's sometimes some choices that get to be made. This is that fun point where things start to be a choose-your-own-adventure in math. So we should write down another rule. Let's see, I think we have enough space. We can squeeze it in. If we're taking the derivative of g of x to the power k, what will that be? This is usually called the general power rule. Okay, so the derivative is acting like x to a power. So you bring the power down, leave the inside alone to the k minus 1. Anything else? Times g prime of x. Now there's lots of ways that things get applied. These are two of the more common ways. So these are things that you're just going to do. And once you practice this enough, it'll become second nature. All right. Well, good. We still have another one. We've done that one twice. So it's not just true. It's twice as true. We definitely know that derivative. Okay, so here we have the derivative of sine of x squared plus e to the tangent x. How do we handle that? Well, notice the plus. What does that allow us to do with derivative? You can split the derivative into parts. So when you see addition on the inside, upstairs, that means, hey, you can really think of it as two smaller pieces. Sine of x squared and e to the tangent of x. We don't usually write this down, but we're doing it right now to get into the flow of it. It's like, okay, I just look at where my small pieces are, take the root of each small piece, and I put them together. Okay, so we won't go through and say this is inside, this is outside. Or at least we won't write it down. Maybe we'll say it out loud. What's the outside function for the first piece? Yes, we saw the sine, and it opened up our eyes. What's the inside? X squared. So when we take the derivative, what are we going to get? Derivative of the outside? Cosine. What goes into the cosine? X squared. Anything else? Times the derivative of the inside, 2x. Plus, because we split it up. The outside? Yeah, exponential, e to the x. The inside? Tangent x. So, derivative of the outside is e. Leave the inside alone. And then, times it by the derivative of the inside, secant squared. And there we go. It's one of those things that once you do it, it's fairly natural. You just have to do it. Practice, practice. Any questions? All right. Well, here's a problem. Find the tangent line to the curve y equals e to the power x to the fourth minus x at the point x equals 1. Y equals 3x minus 2. Woohoo! Yes, you're getting good at this. Nice. So we know how to find tangent lines. So remember, tangent lines store, or if you like, have two pieces of information. So make sure you find the point. You plug in 1, you get e to the 0, which is 1. So our point is 1, 1. We can see our functions, inside and outside functions. So the derivative, e to the function, times the derivative of the function. Again, plug in 1, we get our slope is 3. Point and slope, get our line. Life is good. Okay, good, good. Any questions on this problem? All right. So, one of the things that often happens is that they like to layer these. And so, we've mentioned this before, functions can be like onions. There's layers involved. Now, the thing is, as we add in more layers, we don't need more rules. It's always the same rules. We just have to be patient and work them out. So let's make up some functions. And we can do a couple of these. All right, layer 1. What do you want the first layer to look like? A sine function. Okay, I heard sine. So we're going to find the derivative of sine of, okay, what's on our next layer going to have? Polynomial. Okay, we can have a square root is like a polynomial. Sine of the square root of. Okay, what's our next layer going to look like? X. Let's throw in a tangent. Why not? It probably wants some company. Is that enough layers?
Yeah.
For now, we'll kick it up a notch. Okay, so first thing is, before I take this derivative, I do want to rewrite something. Which part of this should we rewrite to make it calculus friendly? square root. The square root symbol, that's cool if you're back in this is x times tangent x, not x plus tangent x. X times tangent x. That's great if you're back in algebra, but we're in calculus. And our rules work better with powers. So we're going to write the square root as a 1/2 power. How many layers do we get? We have the most inside layer is this x tangent x, which, by the way, that's going to be a product rule when we get there, if we get there. What's the next layer? Well, there's actually the next layer will be the square root. And then it's the sine. So, work from the outside in. Your outermost layer of your onion to the innermost layer. So, our outermost layer has what? Sine. So, if we were doing this in slow motion, and so we go very slowly, we write cosine, right? Because the derivative of sine, spoiler, what's the derivative of sine? Oh, yeah, good. Okay, good. All right, so take the derivative of the outside. What goes on the inside? All of the stuff that was in there originally. So x times tangent of x to the 1/2 power. Times by, now here's where we're doing it in slow motion, times by the derivative of the inside. So normally we'd just do this all in one step. But since it's our first day, we're warming up, we'll do it in a couple steps. Okay, so that's level 1. We've applied chain rule once. Okay, now we're ready for our next layer. So we just copy the first part because that's already been taken care of. Cosine x tangent of x to the 1/2. Okay, so our next layer, what's our outside function? The square root to the 1/2 power. Good. So, what do we begin writing down? Whenever you have something to a power, you say, I see something to a power, the power is coming down. So, what's the next thing to write? 1/2. Inside, leave it alone for right now. To what power?
To -2.
Negative 1/2, right? You can even write it as 1/2 minus 1 if you like. Just remember you subtract 1. But that's negative 1/2. We'll rewrite it as negative 1/2 in a second. Okay. And then what are we going to have? The derivative of x times tangent x. Good. Right, the derivative of the inside. That's our next layer. Okay, so here we go. We have cosine x tangent of x to the 1/2 power. We have a 1/2 x tangent of x to the minus 1/2 power. All right, the derivative of x tangent x.
Secant squared x.
Okay, so it's probably going to be secant squared x, as derivative of tangent x is secant squared. What rule do we need? How do we know it's the product rule? Yeah, because there's a product, right? Hey, I see a product. Oh, I should use the product rule. Ha ha ha. Okay, multiplication product rule. So product rule, everybody needs to get a chance. So we're not taking all the derivatives at one time. We say, okay, is it your turn? Okay, is it your turn? Okay, so, and it doesn't matter who gets their turn first, but everybody has to get a turn. So let's suppose we say, x, it's your turn first. The derivative of x? 1. So you get 1 times tangent of x. So oftentimes we don't write the 1. Plus, now x, it's not their turn. So it just comes down. What's the derivative of tangent? Secant squared. Okay, and then what? Times. Oh yeah, that's it, we're done. We worked our way through it. Now, with practice, you will go from there to there. From that line to that line. Or maybe from there to there. You will skip the intermediate steps, but that will come with practice. I forgot to do a derivative really quickly. I just want to point something out. You might remember we've seen derivatives like the following. Pi to the fifth. Let's apply the chain rule to this derivative. What would this be? I claim this is 5 pi to the fourth is partially correct. If what are we thinking of doing? And what's missing? So that's not the full answer, but I can start by writing that, right? Because I see a power. Power comes down, and I subtract 1 from the power. And then what do I need to do? Multiply by the derivative of the inside, right? But what's the derivative of pi? 0. So it is 5 pi to the fourth, but it's 5 pi to the fourth times 0. So, yay! Consistency. So when you thought about it as 5 pi to the fourth, you weren't completely wrong. You were just forgetting the chain rule. Okay, all right. Should we try another one? Yeah, we have paper. It grows on trees. All right. Let's just write it down here. We have space here. Okay, let's make up another function. Find the derivative of, we need some layers. Is it okay if I just make one up, or do you want to be involved? It's not okay if I just make one up? I got it? You trust me? Oh, famous last words. All right, sine E, let's see. Oh, yeah. We should do x cubed plus sine squared of 3x. Oh, that should be enough. Let me point out one thing notationally. This is a bad thing about notation that we've just inherited. Sine squared of 3x, what does that mean? It's like sine of 3x squared. And the trig functions have this weird thing, and so you have to be careful with your notation and know what things mean. All right, so we've had some time. Is anybody brave enough to read their answer out loud? Okay, I see one person has like, I am fearless. That's okay.
Cosine parenthesis e to the power of x to the power of 3 plus sine squared of 3x and parenthesis multiplied by 3x squared times e to the x to the power of 3 plus 3 cosine squared 3x and parenthesis.
You did pretty well. Definitely a lot of partial credit on that one. So we agreed up until having to deal with this part. So you do indeed get the cosine. Derivative of sine is cosine. Leave the inside alone. Did great with the 3x squared e to the x cubed. Now here, you have to be careful not to take, because derivative of sine squared isn't just cosine squared. You have to say, oh, it's sine inside of a square, but actually it's 3x inside of sine inside of square. It's a triple layer. What? Okay, so the 2 comes down. Inside stays the same. Then you say, okay, times the derivative of the inside. Derivative of sine is cosine. But now, cosine of what? Cosine 3x. So then say, oh, but now I have that layer. And what's the derivative of 3x? 3. So yeah, there we go. There we go. And just a pro tip, right? Parentheses are friends. We like parentheses. So make sure you use them judiciously. For instance, suppose I had not written my parentheses here. So I've forgotten that set of parentheses. Would that be the correct answer? No. The problem is it looks like only this part gets multiplied by the cosine. But you need the whole thing multiplied by the cosine. So that's why parentheses are friends.
Could you go over the derivative of sine 3x squared again?
Sure. So we have 3 layers, right? We have our 3x inside of our sine, inside of our square. So we work from the outside. The 2 comes down. So 2 sine 3x to the 1. So this is the outside. Inside stays the same to the 1 power. Now it's time for the derivative of sine 3x. So start, derivative of sine, cosine. But the inside, leave it alone, still 3x. And then I say, okay, but now I have to go to the next layer, 3x. So I times by the derivative of 3x, which is the 3. All right. Well, our next thing we'll talk about, since we want to get through the theory today, and Monday will be practice, Leibniz notation. Now, this is mostly just side note, but you might say, who was Leibniz? Well, if we were in Germany, we would say, isn't that the calculus guy? And essentially, Leibniz and Newton worked at the same time, and they both came up with ideas for calculus. And of course, it's fuzzy. There were big arguments about who really deserves the credit. But when it comes to notation, Leibniz really knocked it out of the park. Newton had terrible notation. Leibniz, he knew where it was at. And so what's this notation? Well, his was the D-style notation. So the dy dx kind of notation. And so suppose you have a sequence of variables. I have y, which is somehow dependent on u. So y is a function of u. U somehow depends on v. So that says u is a function of v. V somehow depends on x. Okay, so v is a function of x. But if I say that y depends on u depends on v depends on x, we say, well, wait, y really just depends on x? And there's this sort of the intermediate information here. Well, what's really going on here is if you unravel, so we said y is a function of u, but u is a function of v, so that becomes f of g of v. But wait, we said v is a function of h, so that's f of g of h of x. So this is essentially saying, oh, there's a chain of functions. So here's the idea. If I want to know how does y change with respect to x, it's change in y with respect to u times change in u with respect to v times change in v with respect to x. And you're probably thinking, of course it is, because what does it look like should be true? If you just saw this and you were like, what does it feel like? Channel your feelings. Show this to your siblings who are just starting out in algebra. And what will they say? Of course it's true. Because you do what? Because it's like, oh, don't these cancel and don't those cancel? And there's just a dy left and a dx. And you look at them and say, no, but gosh, I wish it were. The thing is, when we write dy du, it says it's not like separate pieces. So you have to be careful. It's not as simple as cancellation. However, that being said, philosophically, behind closed doors, yeah, that's what we do. That's okay. And if you unravel this, you say, okay, dy du, well, that says take the derivative of the outside. That's f prime of g of h of x. du dv, g prime of h of x. dv dx is h prime of x. So this is just another way of saying the chain rule. All right. We have a couple minutes left. Let's try our cool down multiple choice. Our cool down multiple choice problem. Not too bad. All right. F of x e to the power negative 2x plus sine of 2x. And the question is, what is the 75th derivative when you plug in 0? You have a couple of options. And spoiler alert, we don't want you to take 75 derivatives. So you want to do something else. Now, I will point out, if you just saw that part, e to the negative 2x, what happens every time you take a derivative of that?
E negative 2x.
What else do you have, though? Well, you should know from today.
Isn't it just you multiply by negative 2?
You multiply by negative 2. So every time we take a derivative, we multiply by negative 2. We took 75 derivatives, so we're going to have negative 2 to a big number. So we probably should be negative. So that will rule out those two options. So just by that reasoning, it's down to A, B, or C. So now with that, you have a 1 in 3 chance. A, B, or C, what do you think?
B.
We had some B's. I heard some C's. It was A.